Welcome to this explainer. Today, we are jumping straight into a truly fascinating journey inside the human body. We're going to look at the immune system not just as your standard run-of-the-mill defense mechanism, but as a rigorous, highly coordinated training boot camp. Because every single time you get a vaccine, you're essentially sending yourselves through this intense, microscopic military academy. And we're going to break down exactly how this incredible process works, step by step.
Okay, let's dive into this. We've all been there, right? You go to the clinic, you get an intramuscular influenza injection, your standard flu shot, and the very next day, your arm feels like it went a few rounds with a heavyweight boxer. Now, the invisible science of vaccines might feel a bit abstract, but that ache in your arm, that is a very relatable, everyday experience. But what if I told you that soreness isn't a mistake or even a bad thing, but actually the very first sign of a brilliant tactical operation?
Let's start with phase 1. Sounding the innate alarm, the body's early warning system. So when inactive, fraction viral components from the vaccine, like specific subvariant particles called hemagglutinin, actually enter your tissue, they literally cannot make you sick. But to your body, they are entirely foreign, so your body triggers a massive alert by releasing cytokines. These are signaling proteins that act as your primary alarm system, and they trigger a mild, localized stress response. This is absolutely crucial to understand. These proteins dramatically increase local blood flow and actively direct a whole host of other defensive immune cells straight to the injection site. They're basically flashing red lights, telling the immune system's first responders exactly where the breach is.
And here is the punchline. This localized stress response, that increased blood flow, the rush of defensive cells, is exactly why you get a sore arm, or fatigue, or a low-grade fever. Far from being a negative side effect, that temporary discomfort is actually undeniable proof that your innate alarm system is working perfectly. Your biological boot camp has officially begun.
Moving right along to phase 2, gathering the viral intel, featuring macrophages on the front lines.
Now, what's really interesting here is this step-by-step factory process. Once the alarm sounds, the first responders arrive, and these are the macrophages. Think of them as the elite intelligence gatherers of our biological boot camp. Their job isn't just to destroy, it's to analyze the enemy and report back to Central Command. First, they ingest the foreign antigen, like that hemagglutinin particle we just talked about, through a process called phagocytosis. Second, they act like a microscopic dismantling facility, breaking that antigen down into much smaller, manageable components. And finally, they display these broken-down pieces directly on their surface, using a specific receptor known as the Major Histocompatibility Complex, or MHC. They're basically holding up pieces of the invader for the rest of the immune system to examine. Which takes us to phase 3, training the special ops, where T cells enter the fight.
So it's absolutely vital to understand the different types of defenders we have. On one side, we have our special ops, the cytotoxic or killer T cells. While B cells float around in bodily fluids to target specific outside-the-cell antigens, killer T cells operate quite differently. Pathogens will sometimes slip right inside our own cells. While killer T cells actively scan your cells, detect if they'd been hijacked by a virus from the inside, and destroy the infected cell entirely to halt replication. And what makes them truly elite is their broad recognition. Because they target inside-the-cell antigens, even if a virus naturally mutates its surface shape, these T cells can still recognize the mutated threat and trigger a response.
But you see, the killer T cells don't work alone. This is where helper T cells come in. Think of helper T cells as the strategic generals coordinating this entire microscopic response. First, they bind directly to that MHC receptor on the macrophage to receive the intel. Then, they take charge. They stimulate B cells to rapidly divide. They prompt a refinement process called affinity maturation, and they secrete powerful chemical messengers called lymphokines to direct the troops. They are, without a doubt, the masterminds of the operation.
With the generals issuing orders, we enter phase 4, building the antibody artillery, starring B cells and plasma factories. While T cells are busy dealing with hijacked cells, B cells are targeting the bodily fluids. Interestingly, B cells are able to ingest the hemagglutinin antigen completely independent of the MHC, internalize it, and prep for mass production. It's an incredibly efficient factory line. Step 1. Our generals, the activated helper T cells, interact with the B cells and secrete those lymphokines, and these lymphokines serve as the final authorization code. Step 2. This triggers the activated B cells to rapidly proliferate. Step 3. They differentiate into specialized plasma cells. And Step 4. These plasma cells become microscopic munitions factories, mass-producing hemagglutinin antibodies specifically designed for the exact strain of influenza in the vaccine. The coordination here is just breathtaking.
But your body doesn't just settle for making standard weapons, right? It actively upgrades them. This is called affinity maturation. It's a remarkable process where the B cells literally mutate and refine the antibodies they're producing so they bind much more tightly and effectively to the specific pathogen. Essentially, your body is running real-time quality control to make sure its weapons perfectly match the invading threat.
And that brings us to the final chapter, Phase 5, the wanted poster and long-term cellular memory.
Everything we've discussed so far prepares your body for an immediate threat, but vaccines also provide a profound legacy effect through the creation of memory B cells. I absolutely love this quote because it perfectly captures the magic of cellular immunity. If the real pathogen ever invades, these cells remember exactly how to produce neutralizing antibodies, acting as a biological wanted poster. Just think about that. If you're ever standing next to an infected host and they sneeze a live, active influenza virus right at you, your body doesn't have to go through the whole slow trial and error process of a first-time infection. It already has the wanted poster pinned to the bulletin board. It knows exactly who the bad guy is and exactly how to take them down.
And how long does this wanted poster stay up? Decades. Literally decades. These memory B cells, they don't just stick around for a few days or weeks after your arm stops hurting. No! They can persist quietly in your bone marrow and your bloodstream for decades, standing guard, waiting for the exact day that specific antigen dares to show its face again.
Which brings us to the real-world application of all this intensive training, the ultimate defense, blocking live viral colonization in the nasopharynx before disease can spread. Because you went through that biological boot camp, if those aerosol droplets containing live influenza virus ever enter your nose, your nasopharynx, your memory cells instantly pump out those perfectly refined antibodies. They completely block the live virus from ever attaching to your host epithelial cells. The virus is neutralized right on contact, and the overall disease is either entirely avoided or, at the very least, dramatically diminished in severity.
So, we've explored the classic method using inactivated viral components today. But the science of the immune system is literally always advancing. So I want to leave you with this provocative question to ponder. How might different vaccine technologies, like mRNA or viral vector vaccines, change exactly how these crucial training materials are presented to your cells in the first place? Does the boot camp look different when the instructions change? It is a truly fascinating area of modern medicine, and something we should all keep exploring. Thanks so much for joining me for this explainer. Keep those wanted posters active and stay curious.